faster processing speeds, and the advancements in software. It makes it possible to create a software-defined spectrum analyzer, one that is able to analyze higher frequencies emissions at 72 megahertz and 2.4 gigahertz, prepare frequency spectrum baselines, and use frequency spectrum baselines to recognize RF intrusions. The impact that it has in society is that you're going from hardware to software, and so many people use computers nowadays. If they're interested in this technology, they're able to have easy access to it. Also, for our system performance objectives, for our project, we use GNU radio software. This is a drag and drop software that uses modules to simulate portions of the radio frequency hardware. With this, we were able to develop a system algorithm that detects, reports, and monitors signal intrusions in the frequency spectrum. We demonstrated that it's capable of triggering an audible alarm when it detects an intrusion. And we implemented a spectrum analyzer with a waterfall display in the range of 72 megahertz and 2.4 gigahertz. The picture right here that you see is how our system works. The signal on the antenna will receive a signal. It'll go to our digitizer. From there, it goes to our host computer, and here's where the GNU software will analyze the signal, and if it detects an alarm, an audible alarm will go off. For our requirements and capabilities, there's a total of 6, but I'll just be covering the most important ones. The first one is our analog to digital converter. The minimum requirement was for it to work at a bandwidth of 20 megahertz. We were able to go from 1 megahertz to 6 gigahertz. The next requirement is a host computer. The minimum requirement is to use an Intel i5 CPU with multiple core processors with 60 gigabytes of RAM. We ended up using an Intel i7 with 8 core processors and 16 gigabytes of RAM. And the last part is the alarm system. The minimum requirement was to detect and report intrusions. We were able to detect and report intrusions using an audible alarm. And now Martin will continue.
Hi everybody. So here's our layout. It's just a computer and all this stuff. So here's an antenna, right? Right there, this black thing. So that's a 2.4 gigahertz antenna, but we also have a 72 megahertz antenna, and it grabs analog signals in the air, and the digitizer makes it into a digital signal, right? And then it sends it to our computer. That's the computer Raul talked about. It has 8 cores, and it's an Intel i7 and more, right? And over there is our sources. Those are some controllers. So like when those things turn on, we're trying to detect them. When they're on, we want to sound an alarm, like, hey, they're on. So that's the 72 megahertz controller. That controller outputs a constant 72 megahertz signal. Then we have the 2.4 gigahertz controller all the way at the left corner, and that outputs spread spectrum, right? So the signal is sent over many carrier frequencies, not just one. So the signal is sent over many. So that one's a little bit trickier. Next slide. So how do we make an alarm, right? So first, before we make an alarm, we have to get a baseline. A baseline is basically the environment. So like Wi-Fi, your cell phone, all of that. We have to get the amplitude of all the signals so that those don't cause an intrusion, right? Those are the environment. So so we do this either in frequency domain or in time domain. In frequency domain, it's a lot easier, right? So I'm gonna get in here. It looks easy, right, to see the intrusion, but the computer, it's hard for it to detect that intrusion. For us, it looks simple, but for the computer, it's hard. Because the signals are messy, they're hard to store in a variable. So we move it to time domain. And in time domain, these signals are more cleaner. Like our baseline that we had captured is a constant. And constants are easy to store in variables. And it's easier for the computer to know when there's an intrusion. So here's our real signal. And when this signal goes above the red line, then that's an intrusion. And it's a lot simpler. And also, it's automatically calibrated, right? So you can take this anywhere. So in the middle of the ocean, or like Starbucks or whatever, and it'll still work. Because it calibrates itself. Next slide. Oh, so we went with this method, right? Next slide. So here's how we do it. So to capture the baseline, we time this for like about 5 seconds, and we just monitor the environment. So we just look for the higher amplitudes. So here's our HackRF1 source, the digitizer. It sends our digitized data. We convert it to time domain. We pass it through a threshold initially set to 0, and then we store it in a variable. That amplitude becomes our new threshold, and we continuously do it. So when there's a new signal coming in with a higher amplitude, it is stored there, and it also becomes our new threshold. So for about 5 seconds, we do this, and on timeout, we write it to a text file. I know I'm getting in the way, but so we get it, we write it into a text file, and that text file is our baseline, right? That baseline is next slide is what we're going to use to do the alarm system. So we grab that baseline we captured and we put it in the threshold so that all incoming signals are compared to that baseline. So I'm explaining. So we have, remember, this works for two controllers, the 2.4 gigahertz and the 72 megahertz. So the top half is 2.4, the bottom is 72. I will cover the 2.4. So first thing we do is get the signal from the digitizer, and we remove any DC level with the DC spike remover, so just to make the signal clean. Then, because 2.4 gigahertz is spread spectrum and operates over many frequencies, we have to focus on the carrier frequency with the strongest amplitude, and the low-pass filter helps us do that. After that, we have a MUX. The MUX lets us choose between 72 or 2.4. Then, we finally convert it to time domain and compare it to our baseline we captured. If it exceeds the baseline, then we have an alarm. If it exceeds the baseline, we give a 1, and it outputs an alarm. It has an alarm. And then if it doesn't exceed it, then we have a 0 and no audible alarm. And the 72 megahertz path is the exact same thing. And now I'm going to pass it to our team leader, Andrew Long.
Thank you, Samuel. And now I'm going to be talking about our system test results. But before we do, I want to talk about the phosphor real-time spectrum analyzer, or RTSA, with the waterfall display. The importance of this is how it complements the alarm system when an intrusion signal is detected. So again, we're analyzing the 72 megahertz intruder transmitter as well as the 2.4 gigahertz spread spectrum intruder transmitter. The differences we see between these is in the phosphor RTSA, it shows the frequency spectrum versus signal intensity in decibels. Beneath that is the waterfall display that shows us the changes in the frequency spectrum with respect to time. So it gives us a little bit about the history, because without the waterfall display, it would be hard to discern what type of signal is being transmitted, as we can see with the naked eye. Next slide. So this is our Junior Radio software layout. So the importance of this is that this software layout is replacing hardware. So we're able to do prototyping, development, and simulation of software that will emulate hardware, physical hardware. As Samuel said in the beginning, our system layout is just the computer, a digitizer, and an antenna, and this video play. We have a video right here. I think you have to click on it. So the great thing about Junior Radio and our software layout that is emulating hardware is that we're able to have it reprogrammable, reconfigurable, and reusable. So this is our alarm system for the 72 megahertz controller. When we turn it on, we'll see in a bit, it will display a chart on top that indicates 0 or 1. Intrusion has occurred. So yeah, here's the chart, and here's the phosphor RTSA and waterfall display. Right now we're tuned to 72 megahertz, and on the top chart is indicating a 0, meaning there's no intrusion signal detected. So when we turn on the 72 megahertz source, we can see that the audible alarm is being triggered, and that the waterfall display is now showing us the constant transmission. So, and we could also note the note on the top that it's constantly outputting a 1 when the intrusion was detected. But now it's off, so the system returns to 0. So now we're going to get to the interesting part, the 2.4 gigahertz spread spectrum device. The difference between this is it uses the same algorithm, but there's going to be a distinction made of how the spread spectrum signal will affect our alarm system. So we're about to execute it. A little lag, a little early. Okay, so the difference between this is that, like Samuel said, the baseline is recording all the maximum peaks of our environment. And here we see that all that background activity or interference in the background from Cal Cell 8 is not triggering the alarm system. We can note on the top that the system is still outputting a 0. But when we do turn on the 2.4 gigahertz spread spectrum result, we're going to see the effects of it, those intermittent and discontinuous pulses. And it's also important to note that this system is operating at 20 megasamples per second, because that's the maximum sampling rate of the digitizers that we have. So we see that these little pulses, it constantly triggers the system because these pulses are on the order of microseconds. So when we do turn it off, the system does recognize that there is no intrusion signal. That was our system test results, and now I'm going to be handing it off to Kevin Fuentes.
Now let's move on to the passive spectrum analyzer. So the passive spectrum analyzer, it's important to note, it has a much greater bandwidth than the phosphor spectrum analyzer, allowing us to have a greater view of our frequency spectrum. Utilizing the passive spectrum analyzer, we are able to locate the 2.4 gigahertz intruder transmitter's carrier frequencies, which is important because locating these carrier frequencies allows us to feed that information into our software-defined radio alarm system, such that we are able to feed the intrusion signals generated at these carrier frequencies so that our alarm system can then compare it to our baseline capture that we took earlier and set up an alarm whenever there has been an RF intrusion. In this case, the intruder transmissions were found to be located at 2.386 and 2.406 gigahertz. So now let's move on to the system CPU usage. Utilizing the system monitoring tool known as HTOP, we can observe the host computer CPU consumption when our SDR system is either on or off. Search for the following computer attributes. Well, we have the i7 CPU's 8 logical cores, denoted as values 1 through 8 on the figure below. We also have the random access memory, otherwise known as RAM, located on the left-hand side as MEM, and then we have our threads and tasks that are currently on our host computer. Now, in this case, our SDR system was completely off, meaning that we didn't run our alarm system, our baseline capture system, or our intruder transmitter. And this is noted due to the lack of activity in all 8 logical cores, meaning that when our SDR system is off, there is no CPU consumption. Now, if we move on to the next slide, in this case, we had everything on. We had our alarm system, our baseline capture system, our phosphorus spectrum analyzer, and the intruder transmitter. And in this case, we can determine, due to the abundance of activity in all 8 logical cores, that when we have a full load, we consume a lot of our CPU power. So from here, we can determine that it is computationally expensive to run our programs, because our programs are tasking the CPU with a large amount of process, such as displaying the power spectral density, which accelerates the CPU due to digital signal processing. It also tasks the CPU by producing a waterfall display, which tasks the CPU and the GPU for graphical rendering. And our intruder transmitter also tasks our CPU because it's constantly trying to trigger an alarm in our alarm system. And from the figure, we can determine that our overall SDR system has an over 50% headroom, meaning that we didn't utilize the maximum power of our CPU, meaning that we still have a surplus of CPU power left to use. Now for our accomplishments. So it's important to note that we met all of our requirements. We integrated a software-defined radio application on the Linux operating system, and we also implemented an SDR system capable of capturing a baseline of the maximum signal amplitudes. In addition, we successfully demonstrated that our SDR system, or our SDR alarm system, is capable of setting off an audible alarm at the frequencies located at 72 megahertz and 2.4 gigahertz. We also overcame the phosphorus spectrum analyzer's 20 megahertz bandwidth limit, utilizing the passive spectrum analyzer's bandwidth, which is 1 megahertz to 6 gigahertz, and in the end we demonstrated the disruptive capabilities of SDR applications, such that you had to previously use RF hardware for signal processing, or you can now use a combination of computer hardware and software. And that concludes our presentation.